Welcome back to Science Behind the Glass, Illuminating the Human Side, where we explore the people behind the science shaping our future and the chemical reactions that compose our world and make it possible.
Today, we are stepping into the world of atoms, molecules, and massive global impact. Our guesswork might not always make the headlines. It quietly powers the transition to a cleaner, more sustainable planet.
We are honored to welcome Professor Adam, Professor of Sustainable Chemistry at Shanghai Yao Tong University, A-star in Singapore, and Griffith University, Australia. Across his global academic journey from Australia to UK, China, and beyond, Adam has led groundbreaking research in nanomaterials and catalysis, designing tiny structures that drive big changes in how we produce energy, purify water, reduce waste, and reimagine manufacturing.
Adam is not just a scientist, he is a bridge builder between disciplines, between science and sustainability, and between the lab and the world we live in daily.
Who are the characters behind science? This is Science Behind the Glass, illuminating the human side.
In this podcast, we unveil the human side of laboratories and science. Scientists share personal experiences and we discuss their meanings from different perspectives and fields of research.
And thank you very much for joining us today. It's a pleasure having you here in Science Behind the Glass.
Many thanks, Linda. It's my pleasure to be here. Estoy aprendiendo español y me encanta la lengua. And that's the extent of my Spanish so far.
It's perfectly
A
fine.
good start.
And tell us how your journey starts. Why you decided to end up working in not only chemistry, but in sustainability and chemistry and sustainability, how we combine those two. Some people think that chemistry is boring or just too complex. I love chemistry though.
Well, I have to say, I didn't start out being interested in chemistry. So as a kid at school, I had a fairly traditional education, but as a kid at school, I wanted to be a fireman because I didn't realize that they put fires out. I thought they started them, which sounded cool. Then I realized they don't do that. Then in my later on in school, I became very interested in the environment and the natural world, mainly thanks to Sir David Attenborough, actually. So I was a huge fan and remain a huge fan of David. I got to see him speak when I was a school kid at the London Zoological Society, the London Zoo, basically in the UK. But when I went to university, I studied natural sciences to try and expand my knowledge of the natural world and realized very quickly that I was rubbish at maths. So I couldn't be a mathematician or a physicist. My cell biology knowledge was pretty woeful. And that kind of left me drifting into chemistry, which at first, in my first few years of university, I wasn't that interested in. But as I progressed and learned more about things like quantum mechanics, very complex stuff, it sounded cool. And I certainly became far more interested in the use of chemistry for transforming the natural world. And that's kind of where I ended up then doing a PhD in a branch of science called Catalysis, which is a bit of a blend of physics, chemistry, in some cases biology as well. And at first I was looking at, I would say, fairly simple chemical reactions that were hard to match across to the real world around me. So very simple chemical reactions combining only a couple of elements. But then as my research career developed as an academic, I realized that you could use chemistry and catalysis to do a lot of good things for the world, both in terms of cleaning up the environment and in terms of moving away from this fossil fuels that have given us such big problems with climate change.
Oh, that is very interesting. And you have held several academic positions across the world. How has working in such diverse cultural and scientific environments influenced your perspective on global sustainability and the challenges that we are facing today?
So certainly moving around the world, both as an academic where I work and live, but also just networking, going to conferences, visiting other researchers, you realize that many of the problems you focus on in your home country, and I started in the UK for about 25 years as an academic, don't translate directly to the real problems facing people in other countries. I mean, for example, before I relocated to Australia, so I immigrated in 2018, my mental picture of Australia was this giant desert with a couple of little suburban centres, Sydney and Melbourne. I didn't realize it was home to the world's oldest tropical rainforests. I didn't realize that places like Queensland, where I live now, have huge agricultural breadbaskets and we export food around the world. And so when you arrive in other countries, you realize that the resources that are available, the kinds of problems in terms of pollution, for example, vary. Here in Australia and in Queensland, we have the Great Barrier Reef. So issues such as microplastics and their formation and distribution into the oceans is incredibly important. If for no other reason, if you want to look at things economically, then the Great Barrier Reef is a massive tourist attraction and attracts huge amounts of money into the local economies. So it's very important to understand the local challenges and resources. And I'd say that extends, of course, places like Australia and Canada and South America to local knowledge, to people, the often forgotten resource. When I came across to Australia, I went on a trek, a hiking expedition in the Northern Territory. And I realized that there is a real problem with invasive grasses, invasive plants, things like buffel grass. So this is competing with native vegetation. Buffel grass, however, is potentially a source of renewable carbon. So instead of using fossil fuels to make plastics and chemicals, we could use molecules we can extract from buffel grass. But knowledge of these sorts of plants, their life cycles, their distribution, you have to talk to indigenous communities. They understand where these plants grow, their water use, etc. And so that sort of local knowledge is as important as the local resources available in terms of molecules. So yes, it's a real eye-opener traveling around the world and learning about different problems that generally arise because of geography or perhaps local climates.
On this buffalo grass that you mentioned, that one is introduced plant?
Yes, initially. So when the British settlers came across, settlers, aiders, whichever language you used to use, I don't want to discuss politics, particularly in a podcast, but when the British came across, they brought with them cows. So they wanted to graze cattle. So as part of that, many of the local, certainly in the outback, the local grasses, things like spinifex, are very difficult for many, cultivated animals, we call it that, domesticated animals to eat. And so the British brought across with them buffel grass as one of many plants that has come across, which was great for the cows, but it unfortunately competes very effectively with all the local natural plants that have been here for hundreds of thousands or billions of years in Australia. And so although buffel grass is still grown, I think, in places like New South Wales, certain states like the Northern Territories, it is viewed as a pest, a crop, as a plant that needs to be removed as a weed. And so that's a problem which I wasn't aware is not only local to Australia, it's actually local to an individual territory within Australia. So you have these very localized problems or potential opportunities. If you view something like this particular plant, buffel grass, as a source of biomass, it contains lignin and cellulose and hemicellulose, just like all plants in different proportions. But those polymers, those biopolymers, are really useful chemical feedstocks to replace synthetic polymers that we currently make, things like nylon, from fossil fuels. So you always have, in these situations where you encounter a local issue, a problem that needs to be solved, often using chemistry, and an opportunity, both to improve the environment and to make money. It's a source of revenue for local communities.
That's very interesting because I had a chance to work a little bit in a short contract with the Queensland government, and then they had a lot of issues because this buffalo grass is causing also like fires. And then also removing them is costly, but if they repurpose removing this grass for a source of energy, that would be great. And also this led us to other question that is related with the waste valorization. So transforming waste into useful product. So how, besides this example that you give us, how these projects work for you? How can change lives? Do you have an example that you said, wow, this is amazing. This waste really can change lives?
So there's a number of, I guess I'll first say that waste valorization. So waste is what one person calls waste, another person might call a useful commodity. And that's important because for a long time, things like agricultural waste in Queensland, we have huge quantities of sugarcane bagasse that's produced as a byproduct of making sugar for us. these materials were either burned, and they still are around the world. In India, burning of rice straw after the rice has been harvested is a huge problem in terms of pollution. So waste was often seen as a problem, and a way of destroying it might be to simply burn it, generate CO2, a real issue for climate change. Or you might, as you just suggested, potentially transform it into an energy source. You could do a chemical process called pyrolysis, where you heat waste agricultural material under nitrogen, not under air, and so it doesn't combust, but it does transform into a liquid fuel. Now, the amount of liquid fuel you get is relatively low, and it's an energy-intensive process. So really, I guess the first thing to work out is what exactly is waste. And in terms of chemistry, what we're talking about when we're thinking of waste is normally a material where we have to start by breaking chemical bonds before we can potentially remake them to make something useful. Now, waste could be of higher value, and in certain areas where you're talking about agricultural waste, where we have these molecules, lignin, which is a polyphenolic. That means it's a molecule a bit like benzene, an aromatic molecule, and there are many repeat units of this, which makes a polymer chain. Those polyphenolics are actually very valuable chemical commodities that you can transform into things like medicines, into drugs. So if you can transform them into these high-value chemicals, then that's a really, I guess what we'd say would be upcycling, transforming something into a higher-value product. With waste, you could transform it into something. You could put it into concrete, into construction, or into a fuel. So those are sometimes lower value products, but still better than burning it. So in terms of the waste systems that I've dealt with, it's mainly been in this area of biomass. So whether it's forestry waste, so leaves and branches falling off trees that need to be collected, especially in hot climates like Australia, where we have forest fires burning right now down in Victoria State. So actually removing that dead forest material and doing something useful with it has a double advantage. You protect people, livestock, animals, natural environment, as well as potentially getting a valuable product. So there's the forestry waste and the agricultural waste. The agricultural waste is actually of great social value, I would say, not just in terms of things like pollution environments, but as a revenue stream. So a few years back, I worked with the Royal Society in the UK on a project looking at valorizing African waste streams. And there we were focused on Tanzania and Ghana. So I worked with the University of Dar es Salaam and the University of Ghana, looking at byproducts of castor oil and neem oil. So these are crops that are grown across Africa, across the tropics. The oils themselves are not poisonous. They can be harvested and used by humans themselves, but there's toxic residues. So actually ricinoleic acid, a precursor to ricin, an extremely toxic chemical. If anyone's watched Breaking Bad, you will maybe remember the cigarette scene where Walter and his sidekick end up putting this little capsule of ricin into it. Ricin's incredibly toxic. So when you're actually processing these oils for food, you have to be very careful. And you produce quite a lot of contaminated water waste, which has molecules like this ricinoleic acid in. Now, you can therefore, if you work with local communities, as I did and my colleagues, you can try and find ways to transform these molecules, ricinoleic acid, into, for example, a bioform of nylon, a polyester. So these are used for textiles. The shirt I'm wearing is probably 90% polyester, not much cotton in it, and various other uses of these plastics. So polyesters are very versatile plastics. So you've got the option of cleaning up, for example, a water stream coming out of a factory. You've got the option to turn those molecules into a fuel, perhaps biodiesel, to drive a tractor, to power a local community, so it doesn't have to buy any expensive diesel from somewhere else. And you've got potentially, if these components of food waste can be sold on, you've got another revenue stream that can be generated by local communities across Africa. So that was a really cool project, actually getting to see both the raw materials in the wild, on farms, and they often actually grow just on the streets, looking at how the seeds are processed to extract the valuable components that are safe and non-toxic, and then the toxic components that are often just flushed away into river streams, and being able to work to clean up those river streams and make something in your hand, a little beaker of some valuable chemical at the end of it. So that was a really enjoyable case of seeing waste valorization in a local community setting.
Wow, that really brings a new interesting perspective on these so-called waste or residues. And I understand that you also use like some part of the process that is called catalysis of the chemical processes and reactions. Can you explain us a little bit what catalysis is and why it's important for the decarbonizing initiatives and the energy efficiency and the chemical sector as well? Do you think this technology or this part of the process is underrepresented in the climate conversation?
Sure, absolutely. So, in essence, the catalyst is a term we actually use in common society, and it's a term that politicians are always using. We're catalyzing change, etc. So, a catalyst is something that simply speeds up a process. In our case, we're typically talking about a chemical reaction. Now, when I say a chemical reaction, you're probably thinking some large refinery, some giant chemical reactor in steel and pipes. But actually, your bodies are chock full. You have trillions of catalysts called enzymes working away inside your cells and your bodies every second of every day. So a catalyst is simply something that drives a chemical reaction, makes it go faster, ideally without being consumed itself. So catalysts are completely sustainable. At the end of a chemical process, you get the same catalyst back. That's the ideal. Of course, in nature, as in the synthetic world, nothing lasts forever. So plants photosynthesize. That's a catalytic process. They photosynthesize every single day. And every single day, chlorophyll packets that are harvesting light energy decompose and need to be regenerated by the plant. So catalysis doesn't last forever. What it does do, though, is give us a chance to direct chemical reactions to take molecule A and turn it selectively into a valuable molecule, let's say B, and not C. So it can control the pathway of a chemical reaction, and it can also increase the rate of these reactions, sometimes by millions of fold. So reactions, for example, if you have hydrogen and oxygen, two gases, we tend to think of hydrogen and oxygen as together quite explosive. They make a big bang. Think back to the Hindenburg when you had these giant airships flying across. Actually, hydrogen and oxygen, you can mix together and they're basically stable for eternity in the absence of an ignition source, a catalyst, to make the hydrogen and oxygen react together. So catalysts are crucial in all chemical manufacturing now. In fact, 35% of the world's global domestic product is the result of a catalytic process, a human-driven catalytic process. Think about oil, gasoline, kerosene for your airplanes, your jet fuels. Think about the clothes we're wearing. Think about the plastic in my watch. So every plastic, glue, adhesive, paint, solvent is coming from a petrochemical refinery, which is driven by a catalytic process. So we depend dramatically upon these. 95% of all consumer goods that we buy from the shops, our shampoos, our deodorants, and so on, are the result of a catalytic process. So they're incredibly important in modern society. However, when it comes to things like the climate conversation, the focus, quite rightly, is often in things like pollution and environmental pollution. It's trying to understand what the problem is, where it is, the magnitude of it. And so a lot of focus in things like decarbonization in research has gone on ecological studies, for example, or geographical studies, looking at where the temperature has changed, looking at changes in pH or CO2. It's identifying the problem. Now, of course, that's the crucial first step. If you don't know what the problem is, how do you solve it? And how do you get a government to write a new policy to address it? However, knowing there's a problem and being able to solve it are two very different things. Catalysis offers you the opportunity to solve these problems. In the case of things like decarbonization, catalysts can capture carbon dioxide from the atmosphere and they can transform it into something like methane, which you burn, natural gas, methanol, a valuable solvent, or into things like ethylene, a small 2-carbon molecule that's the building block of your polyethylenes. So again, plastic bags, polypropylene, hard plastic pipes. So catalysts are invaluable at being able to capture CO2 to lower the temperature of reactions. Why is that important? Well, our bodies are brilliant at doing chemical reactions at 25 Celsius and roughly neutral pH, and they do it amazingly well. We can't quite compete with that yet. However, every degree Celsius you lower a chemical manufacturing plant, you reduce the energy required from a power station to heat your chemistry. So if you can do reactions lower, which you can do if you can do them faster. So a fast reaction you can do at low temperature. Reactions slow, you generally have to pump more energy in. So catalysts allow you to do reactions with a lower energy requirement, which means less CO2 emissions. So they have a direct impact on things like climate change. They allow you to capture CO2 and transform it. And they also lower the amount of CO2 that is emitted by, for example, petrochemical refineries, or making more efficient cars, so you can operate at lower temperature, more efficient batteries. So a battery is a catalytic reaction at the surface of an electrode. So all of these modern devices that we're used to thinking about, this phone here is doing catalysis as we speak. It's just we don't normally talk about it as a catalyst. We talk about it as a battery. but that's an electrochemical, electrocatalytic reaction occurring. So incredibly important in terms of decarbonization. We can make molecules from biomass from plants instead of coal, oil, and gas. We can reduce the CO2 by using less coal, oil, and gas, and we can even capture and transform the CO2 into something valuable. Very long answer there, sorry.
No, it's
It
fantastic.
is a hard question. Yeah.
Yes. And if we explain the nanomaterials, it's like we can imagine like tiny Lego structures that can be customized at the nano size tools and are designed to help molecules to break apart or join together and into faster and then consume less energy. That's what you explained before.
That's a perfect summary and an excellent analogy, because when we're constructing catalysts or molecules, we often are taking building blocks just like Lego, and the trick is to try and assemble the right bits in the right order to make the more complex structure that we desire. So Lego is a wonderful analogy.
Yeah. So now that you mentioned before, like one of these examples for climate change, can you give us like an example of reduction the pollution or environment and cleanup using these catalysts?
Sure. So I'll focus perhaps. I've already talked a little bit about the Africa projects, where we're looking at taking biomass and trying to find alternative uses for that. Other approaches that are using catalysts now and are getting close to commercial stage are tackling plastics. And plastic is one of the most valuable inventions. It's a class of inventions, but one of the most valuable inventions that humanity has ever discovered. Plastics are ubiquitous, extremely flexible. You can change their temperature properties, their mechanical properties. They're used inside the human body. So, in fact, I have some plastics inside here. I had heart surgery a few years ago, and I've got little bits of Teflon floating around, well, not floating around, embedded inside me to anchor things in valves. So, they're very useful in stents for people who have heart operations to open their arteries. They're used in hip implants. So, plastics are incredibly versatile, not just for your shopping bag or your shampoo bottle. One of the problems, though, one of the reasons that they are so useful is they are very chemically inert in general, which means when they're disposed into the environment at the kind of temperatures and pH and water contents, that they don't decompose rapidly. They can be mechanically broken apart, and that gives rise to microplastics, these tiny sized plastic particles that are easily dispersed in soil or in water systems and aquatic systems. Now, part of the reason that they end up in those ecosystems is because there's no good way to recycle most plastics. So I don't have, often when I'm giving talks about plastics, I have a plastic bottle to hand. I don't have a plastic bottle to hand, so you're just going to imagine a drinking bottle. Those are normally made of material called PET and polyethylene terephthalate. That plastic is actually one of the few plastics that can be easily mechanically recycled. What does that mean? It means that your local refuse collection service, your waste collection service in the city that you live in, can collect those bottles, take them to a factory, crush them, and remelt them and reform them as a new polyethylene terephthalate bottle. However, that's only about 10% of all plastic use. And even there, that recycling process can only be done about 9 or 10 times before the chemical bonds between the polymer chains start changing so much that you have to essentially incinerate the plastic or put it into landfill, which is how it ends up in the oceans. So there's a lot of new research going on. I've got some collaborations in India looking at this right now, trying to use catalysts to chemically recycle plastics. What does that mean? It means taking a plastic chain, a long molecule here, breaking it into its constituent units, the building blocks, like Lego, from which it was originally formed. And that can, in theory, that sort of recycling process can be done an infinite number of times. Because in each case, you're taking the complicated plastic structure back to its most basic building block, which is always chemically stable. So you can always, if you can regenerate that, you can always rebuild the plastic itself. So the challenge, of course, is doing this efficiently on the large scale. By large scale, I'm talking on the hundreds of millions of ton scale. So that's a massive challenge, is collecting the waste, transporting the waste, finding a catalyst and some chemistry that can work at low temperatures, so low energy inputs, and can selectively take this complicated plastic back to its single building block. There have been some very big advances recently around the world at doing this, both with things like PET, but also with polyethylenes, because there are many different types of plastic. Some of these are much easier to recycle than others. One of the problems with plastic waste and trying to tackle this issue is that when you buy a plastic bottle from a shop, you're not just buying a pure plastic. The materials themselves have various additives. It might be a color, blue, yellow, your plastic bottle. That color comes from a molecule, normally an organic dye. That organic dye can poison the catalyst you need to recycle. It might have a plasticizer, something to make the plastic more flexible. So all these additives make it more difficult to design catalyst systems that can regenerate recyclable materials. That's an area that's, I think, very exciting, plastic waste. We know it's a massive problem, so at least we've done a good part. We've identified the problem. We need better ways of screening the kinds of plastics because the human eye cannot tell the difference between PET and polyethylene and polyvinyl chloride. It's very bad at doing that. Machine learning, artificial intelligence, however, does give us ways to rapidly screen plastic waste. So you can imagine a conveyor belt with mixed plastic waste coming in and individual components being diverted to one kind of catalyst or a different kind of catalyst, depending on what their chemical composition is. So there's huge opportunities, I think. In the next 10 years, we're going to see a lot of these processes being commercialized, provided we can set up the infrastructure. And that infrastructure isn't the chemistry, it's that collection. In Australia, we've had issues over soft plastic waste collection. For example, we've had companies collecting hundreds of thousands of tons of soft plastic waste, storing it in warehouses, and the world believing that waste is being transformed and recycled into fresh virgin plastic, and in fact, it's just sitting there in bundles, not being touched, partly because the technology is not very well advanced. So I think we're going to depend a lot on government policy legislation to impose percentages, for example, of recycled plastic that goes into any new plastic material. So your shampoo bottle probably has numbers on it already, maybe 5% recycled, 10% so. It's a start, but of course we don't know how many times those plastics have been recycled. We don't know what waste was generated by the recycling process itself, because that takes energy. And these numbers, 5 or 10%, don't get us away from the fact that we are still using vast amounts of fresh fossil fuels, coal, oil, gas, to make the virgin plastics that we then recycle. And it's typically probably likely we won't top out the amount of plastic usage globally until at least 2050. So we're going to keep taking more pure carbon from the natural environment, fossil resources, expanding that polymer inventory that exists around the world, which gives us greater risk for things like microplastics. Again, a long answer, but it's a complicated system to address.
Yeah, it is. Yeah. And today there is a big emphasis on this thing called nature-based solutions. In your work, do you take inspiration from nature? Are there natural catalysts or natural structures that help your endeavors for energy efficiency or for pollution cleanup?
Absolutely. This will be quite a short answer. You'll be glad. So
Sure.
I've mentioned already about enzymes, human body. So nature has done a wonderful job over 1 billion years of evolution to create these little microscopic chemical factories, you can think of them, that exist inside our cells. And cells, human cells, for example, are great, not just having these chemical factories, but getting different factories to talk to each other, to transport molecules to specific locations within, they're called organelles within cells, to specific factories, enzymes, to do a chemical reaction, to take the product from that first reaction and shuffle it along to another factory, and so on. So this in nature is called substrate channeling. You start with one molecule and you move it along a very well-defined pathway inside a cell so it gets the final product. So it undergoes a whole number of chemical reactions before you make the final thing you want, which might be a complex protein, for example. So in my research, we have adopted something very similar. We take multiple catalysts. In our cases, we synthesize the catalysts from their raw chemical ingredients, and we connect them together in porous structures. So we have one catalyst located in one place, another catalyst in another place, and we connect them with channels, pores, holes, that allow molecules to move selectively between these different catalysts. And that allows us to control the sequence of a chemical reaction. That's important because, one, we make only what we want, and that means we minimize waste production because all of the atoms in our starting material end up in the final product. We don't make byproducts. And it also means that we can do reactions very quickly at low temperature. We don't have to worry about trying to alter the reaction chemistry by changing reaction conditions. We just change the location of our catalysts. So this idea of substrate channeling can be translated directly into artificial biology, if you like. So we're doing chemical reactions in the lab instead of inside the human body. And we've used that to make a number of precursors to things like artificial sweeteners. So doing oxidation chemistry to make things like aspartame, which if you look at your NutraSweet and these various precursors, you will have seen this molecule before, and also pesticides. So pesticides are very important, not just when we think about them in controlling crops, but then from a social perspective, allowing populations to expand. I should have mentioned earlier probably that the most important example of man-made catalysis in the world is the production of ammonia. So roughly 5 billion people on the planet of Earth today are alive solely because of the industrial chemical production of ammonia, which is a precursor to artificial fertilizers. Without that, those artificial fertilizers, we couldn't grow sufficient crops to support a population above about 3 billion people. So a lot of us owe our lives directly to this process, which was developed by Haber-Bosch, or two scientists, Haber and Bosch, over 100 years ago, two German scientists. And it's often cited as one of the biggest civilization advances, discoveries that's ever been made. We're still optimizing the process. We still tweak the formulations of the catalyst, but in essence, taking nitrogen and hydrogen to make ammonia, something you don't think about, is incredibly important for society. It's not just cool chemistry. It allows people to live.
Yeah, that's amazing. And that led us to the following question that we have, that is how the sustainable chemistry is helping with equality, with with food security, water security, and underserved communities. How we can transform all these sustainable chemistry in simple ways that people can have access to a better quality of life.
Absolutely. And so that essence, that idea that science, discoveries, engineering, that humans should try and contribute to a betterment of society, that's all encapsulated in what's known as the United Nations Sustainable Development Goals. So these are 17 goals that were set by a large committee of people from all different countries with the hope that we would achieve these 17 goals by 2030, which is now only 4 years away. We're not very close, but amongst those 17 goals, there were, for example, the idea that everyone in the world should have access to cheap energy, sufficient nutritious food, to clean water. Now, sustainable chemistry is actually critical to all three of those. I'll start with, for example, looking at the idea of clean water. So catalysts play a role twofold. One is trying to make valuable chemicals. I talked about the work in Africa, trying to clean up food waste streams where highly toxic chemicals are discharged from farming processes into water. So you can make valuable products from those toxic chemicals. You can also take catalysts that can, for example, capture sunlight. They can harvest sunlight and use it to split water to produce very strong oxidizing agents, a bit like bleach, but made directly in situ during the reaction. So you can take sunlight, use the energy of the sun to produce peroxide radicals that can decompose any toxic chemicals in water. And so this sort of photocatalytic, it's called, where you photo from light, catalyst, because you're doing a process very fast. That photocatalysis is used to clean up wastewater streams around the world, particularly places like India, where you have a lot of organic dyes that discharge from textile factories into river systems that could contaminate people's drinking water. Or, and we don't often think about it, but what happens when you take your dose of medicine? What happens when you take your paracetamol, your acetaminophen, and you take a bit too much of it? Not enough to do any harm to yourself, but enough that it doesn't all get processed by your body. What happens is that it gets excreted into your toilet, into the sewage system, and so you end up with river systems that are accumulating pharmaceuticals that the fish end up consuming that wasn't designed for fish consumption, and you end up causing mutations in the aquatic system. So these are called xenobiotics, things like antibiotics that we take as well. Penicillin, you take too much, it doesn't do any harm to you maybe, but it actually does harm to the fish. So photocatalysts, which are often made of semiconductor materials great at capturing light and exciting electrons and what's called holes, and these are very reactive species. So those can react with water surrounding them and are used to clean up contaminated wastewater systems. So photocatalysis is a direct means to very cheaply, so there's no moving parts, there's no energy input from heating something, burning something, literally just sunlight, in a plastic bottle with a little white powder. Typically titania is used. It's a non-toxic pigment that's in all the paints around us. The wall behind me had lots of titania in it. This is actually a very good photocatalyst. So very cheap technology that can be deployed at scale around the world in emerging countries. Then you have, we mentioned about the idea of fertilizers from ammonia, but you also have pesticides production. The pesticides are critical. We've said about viruses, but we have many issues with microbes, with pathogens, with insects, things like termites. So one of the molecules I was talking about, or my group has been working on, is the production of something called cinnamaldehyde, crotonaldehyde. These molecules that contain a carbon-oxygen bond are actually very effective at termite deterrence. And maybe termites aren't too big a problem in the UK, but when you come out to Australia or in Africa, termites are a huge problem, both in terms of the damage they do, but also in terms of the resources they consume, the vegetation they destroy in terms of crops. So you've got, a real issue there, not just them destroying homes. So if you're looking at food production, waste management, then catalysts are going to be critical to meeting these United Nations Sustainable Development Goals. There's many others of these, aquatic life as well, but those are the core essences.
Many of your projects also involve developing materials that can clean up pollution and the things that you were talking to us for just right now. Can you walk us through a moment when you saw directly the human impact of this work?
So obviously the projects I would say in Africa have been the most direct. However, in terms of sustainable chemistry and catalysis in its broader context, which is basically a chemical reaction, it doesn't have to be to make a consumer product. One of the projects that I worked with a while ago with a big medical company was actually looking at trying to develop antimicrobial dressings. Antimicrobial resistance is a huge problem globally, millions of deaths every year, particularly from things like hospital-acquired infections. So if someone goes into a hospital with one illness and contracts something like MRSA, methicillin-resistant staph, and ends up dying from the infection they acquired inside a hospital. So treating these resistant bacterial strains is a huge problem. Discovery of new antibiotics is slow and takes a very long time. However, there are many materials, for example, silver and copper, have been used for thousands of years. The Romans used to have very expensive, not my little china cup, they would have silver drinking cups. Why? Because they realized that when they had something made of silver or copper, bugs didn't grow in it. It would keep your wine fresh for a long time. So I've done a lot of work trying to develop materials that can control the release rate, the dissolution of silver and copper ions into things like wound dressings for patients. So the work I was doing, this was mainly back in the UK, was focusing on burn victims. And in hospitals, if someone goes into a hospital because they have a burn, they will often have a dressing on their wound. And that dressing sits on skin, which is very, very delicate, incredibly painful when you remove these dressings. So really, hospitals are looking at ways to have dressings that can keep a wound clean, free of bacteria, and don't have to be changed very frequently. So I was working at trying to design nanoscale composites, little porous materials, think of them as tiny sponges that would contain silver in the form of, for example, silver carbonate. And when in contact with the human body and tissue fluid that's released from wounds, they would slowly, very slowly release a controlled amount of silver that would keep the wound clean, free from bacteria, without releasing too much that it would turn the patients blue, which is a side effect if you consume or are exposed to too much silver, and most people don't want that. So that was actually a really exciting way of working with both the medical manufacturers of these dressings, but also some of the people who would look at the formulation. So we would make the raw materials in our lab. They have to be incorporated into different polymer formats to then go into a final wound dressing. So working with some of the small companies there, looking at the production lines and issues that arise when you try to scale a technology that could have a direct impact on human health. And so obviously burns are terrible things. They're very, very difficult to treat and requires a long recovery period. So that was a really nice way of doing something very different. Not a chemical method to benefit, for example, a large company, a large chemical manufacturer, but something to benefit humans directly and alleviate suffering. So that was, I think, for me, a cool project to work on.
That sounds fantastic.
Thank you.
And if you could redesign one of the global products, for example, a phone, a car, a shampoo bottle, through circular chemistry, what would it would be? And what would this product life cycle could be redesigned or could be changed?
So there's many problems, I guess, that are already being tackled by a lot of people. So I mentioned plastics. Although I do research on plastics as well, there's a lot of people around the world working in that field. So the plastics field incredibly important, particularly for this whole circularity. But there's one area that I've started looking into, published a paper with recently, on another area that's actually a new problem that we're creating as a result of trying to solve another problem. What am I talking about? Renewable energy. So we're all aware burning fossil fuels bad. Okay, great. How about I stick a solar panel on my roof? I'll capture sunlight and turn it into electricity and power my air conditioning. Bit of Australia, you need it. Don't in the UK in general. Aren't I good? Well, yes, you're good that you're not burning fossil fuels, but what are these solar cells? They're typically called photovoltaic solar cells. They take sunlight and convert it directly into volts. Photons to volts. And they're mainly built from crystalline silicon, very high purity silicon. The problem is that they have limited lifetimes. You can put them on a roof, but after 10 years, with the current technologies, they have to be disposed of. And extracting that silicon and finding any value for it is extremely difficult. By 2030, it's estimated that China alone will be generating 1.5 million tons of silicon solar panel waste per year. So that's a vast quantity. That, of course, includes some plastic components that might hold things in place, a little bit of glass, but most importantly is that silicon part. That's the high value part. We don't have any good solutions for recovering it. You can try and crush them mechanically and then stick them in a landfill. That's not really recovery at all. That's just disposal. Doesn't solve a problem. There are chemical treatments to try and extract metal components. For example, you might have copper wires that take the electricity out from the silicon, or gold wires. But those extraction methods often use toxic solvents to dissolve the metals. So chemical recycling isn't very efficient. So I've been working quite recently with a group in China at looking at very fast heating of these crushed units in the presence of dirt, okay, or more technically, carbon. And now carbon is something that is pretty abundant all around us, the entire world. All our fossil fuels come from it. Biomass is the core of all plant life on the planet. So carbon is actually quite cheap to access. Now, why would you want to do that? Well, if you heat very, very quickly these crushed units that contain all sorts of complex mixes of things, the silicon inside reacts very fast and selectively with the carbon component to make something quite simple called silicon carbide. Now, silicon carbide is itself a very useful and high value material. It's used in mechanical gears. It's extremely hard wearing. If you buy tools, a pair of scissors or something from a hardware store, they will often have silicon carbide in. It's also used as an electrode in batteries. So although this isn't a classic example of what we would call the circular economy in terms of recycling, turning silicon solar panels back into silicon solar panels, it is an opportunity to take what is now a huge waste stream as a result of trying to do something good in using renewable energy, a huge waste stream that's growing, and using that as a source of lithium-ion battery electrodes. And battery usage is also growing at an exponential rate. So we know batteries are continuing to be increasingly important around the planet. And if we can find cheap ways, taking a waste material, the silicon from our solar panels, turning that into a very high purity silicon carbide, which you can do over 98% pure silicon carbide. And when I'm saying about this heating, the energy input is very small. We're using a technique called flash joule heating. You basically put an electric current for a millisecond, literally 1 millisecond, through your silicon and dirt mix, and it makes very high purity instantly. So there's a spike of temperature, goes at 2000 Celsius in a millisecond, cools back down, and voila, you have a pure piece of silicon carbide. So very effective, very fast, very low energy input because you're heating them so quickly for such a short period of time, you actually use very little energy, and it's scalable. And that's very important for any new technological discovery. It's okay doing something inside a beaker, my coffee mug at a small scale, making a few grams, but with this sort of waste where you're looking at the millions of tons, any new technology has to be cheap enough and simple enough that you can deploy it, you can use it in the real world at very large scale. So that's an area I'm really interested in. It's, again, a case of really what we call upcycling. But at the end of battery life, batteries themselves, there's a lot of technology to now separate the metal components from the semiconductor, silicon carbide type components. And so although you might not regenerate a solar panel an infinite number of times, you might turn it into a battery that could itself be regenerated many times without having to go and get fresh metals out of the ground, without, again, raiding the earth. And that's particularly important in things like batteries where we're using earth-scarce metals. So sustainability, I've been talking about chemical reactions quite a lot. But actually in sustainability, one of the core concepts is trying to minimize natural resources. And that means often working with materials that are abundant. Things like aluminium, silicon, zirconium, that there's lots of in the Earth's crust, so we can easily extract, and not things like cobalt, lithium, where we might have to go deep down below the Earth's crust and even into the ocean bed and start trying to harvest there, which could cause untold damage. So if we can use abundant elements that are around us, it minimizes environmental impact and makes things cheap. Cheap technologies, companies, governments like. Expensive technologies, even if they work, nobody likes. Okay.
Yeah, that's very true. And actually, it helps to our next question because all these technologies are very promising, but as you were saying, they have their limitations in several ways. Even, for example, in the medical use, you have the legislation and the security for patients and everything to to be implemented and to be approved. So where do you get like the hope in your projects and for the future as in general? How do you think we can address the future as scientists and young scientists coming next?
So I would have to say my answer is probably a surprise to me as much as it will be to you, in that normally academics particularly are great at saying, my research and my idea is the best. I can solve all the world's problems. I'm actually going to point the finger for the hope to the opposite arena of academia, social sciences. So what I would say, and the reason for that is quite simple, money. So one of the big challenges, of course, is getting global agreement to solve any problem. Climate change, the big problem is that we still don't have global agreement for emerging and developed countries. Why? Because the developed countries don't want to actually do things that might be more expensive, and the emerging countries want people who've already benefited from resources to try and to be subsidizing the people who haven't had those opportunities, to make everything equal. So I think really developing economic frameworks for example, renewable energy technologies are going to be critical, because we already know that we can make solar panels and wind turbines and wave machines that can actually meet the vast majority of Earth's electricity needs. That could be done tomorrow if there was a government will to do so, a global government will. There isn't a global government will because it's expensive to do. And yes, there are other interested parties from the fossil fuel sector who lobby governments very strongly, but they're able to be successful in lobbying governments for slow change because our alternative technologies are not cheap. Why aren't they cheap? Because we don't, as physical scientists and engineers, as a chemist or a physicist, I don't have the ability to construct a business case that will convince the Australian government that we should install 10,000 wind turbines. So that's a crucial gap, I think, between when we're talking about real research problems and real interdisciplinarity. It's not a chemist talking to a physicist. It's a chemist talking to an economist and sitting down and doing what's called life cycle assessments. What's the real impact in terms of energy consumption, CO2 footprints? Where does the power come from? Where does the resources come from? And doing techno-economic analysis as well, looking at how the costs scale. What's the biggest component? If I'm building a chemical factory, is the most expensive thing for that factory the raw materials, the chemical molecules that go in and out? Or is it the capital, the steel pipework? Or is it the resources, the people, the human resources? All these things are critical to making a business case that will convince the government to set legislation to, for example, change subsidies for producing biodiesel versus fossil fuels, for setting thresholds on the percentage of renewable plastics that should be incorporated into any new piece of clothing. So surprisingly, it's yes, the scientific discoveries are crucial. And the next younger generation are doing amazing strides in doing that. They now have access at their fingertips to essentially all the world's information through the internet. And with machine learning and the ability, even with things like ChatGPT and all its problems of hallucinations of answers, there is still the ability to access information and to identify solutions in a very short time scale that has never previously existed on this planet. So I think the next generation will be able to make discoveries very quickly, partly through things like machine learning to rapidly identify chemical conditions, catalyst materials, that can be rapidly tested in a lab on a timescale thousands of times shorter than normal. The same perhaps for drugs, for pharmaceutical drug formulation. Rather than having to do trial and error of thousands of combinations of molecules, a computer will very quickly tell us which ones are likely to be feasible in a split second. So we have that sort of ability. But I think also the younger generation, I hope, are exposed to less rigid boundaries at education level than certainly I was in the generations before. I was taught, and I don't regret it, but I was taught formally at school, chemistry in one lesson, physics in another, and biology here. And even at university, I went to study natural sciences in Cambridge, but I was still forced each year to choose chemistry or biology, or this is how courses are taught. And that siloing, that separation of knowledge is something that has changed a lot. Most schools now don't teach individual sciences. They will teach science as a collective. There has some disadvantages of that. They might not know what a chemist is because of that and what chemistry does, but they will be more aware of other areas outside of their core disciplines. And that ability to speak different languages is critical. I talk and interact a lot with chemical engineers. I've had to learn a lot of engineering language. And those skill sets that the young scientists and engineers are getting now will be invaluable in solving these real global challenges, which no one, a chemist alone cannot solve, a physicist alone cannot solve. And so I'm hopeful that if there is true communication between scientists, physical and life scientists, engineers, and social scientists, people who will actually dictate policy to politicians. It won't be us. It won't be a chemist writing a policy statement. It's very unlikely. It might well be a social scientist or an economist who writes a policy statement for a government. That communication will allow us to make good business cases and to propose technologies that are implementable, not just pie in the sky, some fantasy idea, but something that could be put into practice in the real world.
Yeah, that's true. Actually, something that is really important is now that you mentioned the working or collaborating with other fields, for example, economy, and like trying to not only see it is feasible, but also thinking in the future, no, in the immediate future. How much is going to cost having all these waste, electronic waste, for thinking as how can we cycle or how we can design a product that actually we can collect everything after the end of the cycle of that particular product, and then making like the numbers around of how much is going to cost clean up the mess that we did with that, for example, with solar panels that if they don't recycle properly, they're going to become just waste. So yeah, you have a huge point. And then to finalize, we want to know what has been, although you mentioned some of them, what are the challenges that your work that you have in your lab work, and what would be a message that you have for the public?
But the message, the answer I'll give now has probably changed dramatically. 5 years ago, I would have probably given some scientific type answer, something maybe technical. But the world has changed a lot. Actually, to be honest, it's changed a lot in the last decade. There are reasons and individuals we could name for that, who I won't name. But we have to live with today's reality. And the reality is that the general public and many governments and politicians now see universities and even government research organizations as ivory towers, homes of the elite, people who just want to sit around and think and contribute nothing to society. That's the message the public has been receiving from many individuals and groups around the world. That's a very bad message. The reality is that universities and government research institutions are the knowledge bases of civilization. Okay? They are responsible for almost all the technological advances that we've seen benefit modern society. That could be from the internet to the synthetic production of insulin that saves the lives of diabetic patients around the world every day. It could be from the construction design and placing into space weather satellites, which now allow us to predict extreme weather events well in advance and save millions of lives every day. Well, every day, every year at least, by being able to predict when cyclones are going to hit a coast, damage crops, and so on. To things like cancer therapies, the ability to treat, a third of us in our lifetime will certainly have some impact of either heart disease or cancer. Probably every one of us in our lifetime will know a close family member who has a form of cancer. So these therapies are coming directly from universities. We often talk about private corporations. Private corporations are invaluable, and private-public partnerships are very important. But the vast majority of private discoveries are building upon either researchers training in universities or ideas generated by universities. We've seen that recently with the COVID vaccines. But if you go back to the original research, where was it conducted? Who funded it? In general, places like the NIH funded it in America. It was government-funded research that then private companies took out and turned into a workable vaccine. Very good, glad they did. But we still have to recognize that the government-funded research is critical. Why am I saying about it being critical? Because despite it underpinning our way of life, that government-funded research globally is still woefully underfunded, and the role of experts in society is often undermined by politicians or public figures who say, don't listen to the experts. That's a terrible message, and that does a great disservice to society. And so what I would say the biggest challenge really is trying to ensure that every country should have a high quality education system running from kindergarten right the way through to tertiary education through to university. Why? Because it equips society, then the public, with the skills to understand what is truth and what is misinformation. So trying to explain complex scientific ideas and their importance to people who never had the opportunity to understand basic science, for example, is a disservice to everybody. It won't work, and it's not the people's fault. They were denied a high quality education. And so really, I think when we actually have a population that is well educated, is able to make decisions themselves with the right information, then they will vote for policies that will benefit the many and not just the few. So sounds a bit political there, my slogan. But that's something I really strongly believe is that that's the biggest challenge, is educating the public so they have the tools to understand when people are trying to deceive them or confuse them, and to appreciate the value of scientific research and technological discoveries, which often is long-term. Many discoveries that we know, things like the blue laser, took maybe 30 or 40 years to come into effect. There's many discoveries that are sat around in labs, but without that discovery, we would not have them today. We would not have the correct lasers for doing medical operations. We would not have our fancy phones and so on. See, there are huge, infinite number really of examples. But a lot of people don't appreciate the value of core science. And the GDP that some countries like Singapore and Korea invest, 4 or 5% or more, is very impressive and gives them a chance. It's why they're now front runners, in the scientific field. It's why when you look at league tables, Chinese universities are going up and up and up every year. It's not coincidence. It's a huge government, national devised investment program, putting billions and billions in, because it will have rewards. And when you look at the country that's generating the most patents in the world now, China's just about overtaking the US. So it's not just about core science and publications, it's about inventions that will become commercial products. And so I certainly, for the Australian government and in the past the UK government, would love to see more investment there, because that's what it is. It's not just cash going to universities and CSIRO, it's an investment. And there will be a return on investment, and that return will be huge. But if you don't invest now, you won't have the solutions in 40 years' time that we're all desperate.
Yeah, I
It's a
completely
very
agree.
important message. Yeah.
Yes, yes, thank you very much. I think that one of the things I will add is like not being passive as a public, for being more active. Now that, as you mentioned, we have access to the information in a way that we didn't have before. Yeah, there's a lot of misinformation. Education could be amazing for everyone if it were free.
Yes. Yes. And that was
And
the subtext buried in there is that everyone should have a high quality education, which means really it has to be free and not the best education only for the wealthy. So, yes.
thank you very much, Adam. It has been amazing having you here. And with all the knowledge, I was just like paying attention. I was like, oh my God, that's so nice to understand and so simple.
Thank you. Thank you very much. It's been great chatting to you both.
This episode took us to the heart of science that works in silence.
Adam's work shows us that sustainability is not an abstract concept, but a chain reaction that starts in the laboratory and ends in the world we live in daily.
Remember that Science Behind the Glass now lives in a new platform that connects the podcast to all major streaming services via RSS. Just click the link in the description to find us on Spotify, Apple Podcasts, Amazon, YouTube, and whenever you love to listen.
Science Behind the Glass is an independent podcast created and hosted by me, Daniel Esguerra, and Linda Hernandez Duran, with the invaluable support of our technical director, Rafael Giordano, and the original music by our dear friend and colleague, Bernardo Aguilar.
Follow us on Instagram, X, Facebook, LinkedIn, and TikTok, and visit our website for more stories, updates, and resources.
Don't forget to subscribe and share this podcast with your friends and communities. Let's amplify these essential narratives together.
And if this episode inspired you, consider supporting us with a contribution via PayPal. Just click the Support Us button on our website. Your support helps us to grow and ensures we continue illuminating the human side of science. Until next time.